How is everybody doing? Chemistry 240. This is the second to last chapter in this particular course for Organic Chemistry 2. Chapter 20 is a very comprehensive. I know that it might be after chapter 19, we are kind of exhausted and really tired of mechanisms. So the good news for chapter 20, well, there is good news and bad news. So the good news is that there are not really maybe one or two mechanisms for chapter 20. But as opposed to chapter 19, that were like at least like 8 reactions that we needed to learn. Now for chapter 20, we actually multiply that reaction list to about 15, if not 20 reactions. Okay, so that's maybe the challenge for chapter 20. I know that for chapter 19, I decided not to include that many questions about synthesis. That doesn't mean that we will not have synthesis. If there is synthesis, maybe you guys will do a synthesis involving 1 or 2 steps maximum. But for chapter 20, we have a plenty of reactions. This is a lot to memorize. To me, really is a chapter that is easier to teach, but from the student side, of course, it's not that easy because you guys have to memorize all these reactions. The only way I was able to remember those reactions is by repeating and repeating. And then depending if you're taking this class in the summer or you're taking it during the regular semester, still a very limited number of hours that we can dedicate to studying and memorizing all those reactions. Okay, so let's do our best. Let's see how we go with this carboxylic acid derivatives. This is just to give you some housekeeping rules for this chapter 20. Just telling you like what to expect, right? And what to really, how to address this particular chapter. Okay, so it's mostly memorization. We will have some synthesis problems, but once again, just simple ones. Like so simple, maybe one or two conversions that will be for our synthesis. And then the base, the foundation for those synthesis, of course, will be learning the reactions. Okay, carboxylic acid and the derivatives, as we see here, the main functional group that will be covered, it will be the carboxylic acids. We know how carboxylic acid look like, right? So this one is the most basic. Well, this one is smaller than that, so which is formic acid. I don't know if you guys have heard about formic acid. Formic acid is the one that has no carbon, no side chain carbon. This is formic acid with an oxygen here. You can see the carboxylic acid functional group, right? On this side, this is the carboxylic acid functional group, and then there is an H. It's called formic acid. Formic acid is present in the poison of ants, I believe or not. So you guys have some redness or some swelling after being bitten by an ant. Definitely that's formic acid. It's a self-defense mechanism that some animals have, mostly insects. So formic acid is the smallest carboxylic acid that we know. But the most commonly used is acetic acid, which is for vinegar, right? The pungent smell of vinegar is coming from acetic acid. We have uranoic acid, and where we find it, hexanoic acid, and then lactic acid, right? So which is the taste of sour milk. So once milk goes bad, yeah, that's what like the buildup of lactic acid. Lactic acid for the people that also is a lot into exercising and then like stretching. Lactic acid is the incomplete metabolism or the incomplete degradation of sugar. So lactic acid is one of the steps of the degradation of glucose, right, in the cell. So if we don't breathe enough, you guys will start building up a lactic acid in your muscles. Lactic acid is a solid. So once you guys do not fully degrade by respiration, right, oxygen, right? So for example, I'm running, but then I don't breathe enough. So I'm not giving to my cells the oxygen that is needed to degrade uh, the lactic acid. So what's going to happen in my cells if I don't fully degrade lactic acid? Of course, lactic acid will build up, right? It will accumulate inside of the cells. The bad thing of lactic acid is that at high concentrations, it can crystallize pretty nicely. And the shape or the way how lactic acid crystallizes is in the shape of a needle. So that's why after a full day of exercise, for example, I don't exercise for about a week. Then I decide to exercise, but I don't breathe enough. So what happens? The lactic acid will be it will be inside of my cells, and then I will have that pain. I don't know, you guys feel some pain in your muscles, like, oh, I just did too much workout yesterday, or the 10 hours before, the night before, something like that. So it's because of the lactic acid. So to prevent that lactic acid formation in the cells, is appropriate to have a good breathing and respiratory technique. Right? So in the industry and pharmaceutical applications, we have acetylsalicylic acid, which is known as aspirin. You can see here the carboxylic acid, aminosalicylic, and it is used for many, for antibiotics, to kill germs, right? In general. So why? Because of the acidity. And then we also saw some other type of functional group, which is the aromatic group, right? The benzene ring is present. We already discussed, right? This is not a benzene, but we say that in a lot of pharmaceutical products, pharmaceutical companies use it in many of the drugs because of the hydrophobicity. Carboxylic acid are actually very hydrophilic, meaning that they're very polar compounds. Okay, so they're very polar functional groups. So, for example, in this compound, the polar head could be the carboxyl group, and the hydrophobic body, right, could be the benzene ring. Esters, we will see esters in this chapter as well, is one of the subfamilies, what we call the derivatives of the carboxylic acid, because they all come from the carboxylic acid. Okay, so here there are some more about carboxylic acid. Carboxylic acid is also an sp2 carbon, therefore is trigonal planar. So the reactions that are mostly associated with carboxylic acids are the substitution. We're going to be substituting. The COO will not do addition. As opposed to aldehydes and ketones, chapter 19, we were doing mostly addition reactions, right? You recall addition reactions. Now, in this case, we will substitute. So this OH will get lost. We keep the R and the COO group, but then this group will be substituted, okay? So if it's an OH, it's a carboxylic acid. If it's an OR, it will be an ester. If it's an NH, it will be an amide. If it's another OCOO, that will be an anhydride. And if it's a halogen, it will be a acyl halide or acid halide. Okay, so in terms of the physical properties of carboxylic acids, we can see like a huge difference in boiling point. Acetic acid has a boiling point of 118, whereas ethanol, a conventional about the same size of alcohol is 78 Celsius degrees. You say like, oh, wow, that is like about 40 degrees difference. So what is responsible for that increase in boiling point? Well, there are many reasons. Well, first is that the carboxylic acid they're good at forming and accepting, right? Is a hydrogen bond donor and hydrogen bond acceptor with hydrogen bonding. The hydrogen bonding occurs at the level of the OH and also at the level of the oxygen of the COO. So this COO is also able to form hydrogen bonding. This oxygen forms hydrogen bonding, and that H forms hydrogen bonding. So it has many donors and acceptors. Whereas the ethanol only has one OH, right? So this OH would be about the same, right? In terms of like strength of formation for hydrogen bonding, but carboxylic acids, in addition to that, they have that particular COO that increases not only the dipole-dipole interactions, but also the hydrogen bond formation, right? Capacities from that COO, right? So that really explains why acetic acid, carboxylic acids in general, they have a higher boiling point than their, similar, right? Compounds similar in the sense of size in alcohols, right? So, yeah. Let's keep going. So here, carboxylic acids, they are, as the name says, acids. If they're acids, that means that they respond to bases in an acid-base equilibrium. So here you can see that the NaOH, sodium hydroxide, the OH extracts, right, or pulls off the hydrogen, and then you form a carboxylate. Carboxylates are soluble in water, regardless of the nature of the R group. So even if this one is a benzene ring, which is very hydrophobic, but the polar head, the carboxylate, will make it soluble. That's the principle of detergents. Detergents really belong to the family of the carboxylic acid. So this is really what a detergent is. A detergent is like a really long hydrophobic chain, and it has a polar head. That is a carboxylate. So it will remove, this is a detergent. It will remove any type of a stain, grease, ink or anything by using this polar tail. The polar tail is the one that's going to be responsible, right? So you have some ink or some compounds, dye, wine, whatever, right? It will be trapped by or attracted by this, alkyl chain, carbon chain. And then the polar head will be responsible for the water solubility. So water soluble. So that's how you can extract, right? Or you can remove the dirt and the stains from clothing or fabric or plastic, right? In general, using detergents. Okay. Now in detergents, it's a totally separate chemistry. We have the anionic detergents like this one, and we also have the cationic detergents. Okay, so the cationic detergent is the opposite. So instead of having like a negatively charged polar head, they have a positively charged polar head. Okay, so those cationic detergents are a little bit more expensive, that they say that they're also more efficient. Okay, because they have cationic, they use nitrogen, they can have more hydrophobic, right? More of these guys, multiple of that. So they can trap more dirt and grease. Right. So in terms of the carboxylic acid, as we were saying, so there is a group here, COOH, and then this carboxylic group will have, different opportunities to form hydrogen bonding. So it can form hydrogen bonding through this lone pair, through this lone pair, this lone pair, this lone pair, and of course the hydrogen that is also able to form hydrogen bonding. Supposed to the alcohol, right? The alcohol does not have that. I mean, it has many. It's very good at forming hydrogen bonding, but in terms of number, yeah, you can only form 3 potential hydrogen bonding, whereas here you can have 5. Okay. Now, in terms of the acid-base properties, right? So, a good way how to make carboxylic acid soluble is by adding sodium hydroxide. Right? As we saw in the slide. So you guys will form carboxylate. Okay, but sodium hydroxide is not the only base that can be used. There is a weaker base that can actually be used instead of sodium hydroxide. Why? Because carboxylic acids are so acidic that they're even able to respond to weaker bases. What are those weaker bases? Those weaker bases include sodium bicarbonate. That's also another one that is commonly used, or sodium carbonate. They are less basic than sodium hydroxide, but they can still deprotonate the carboxylic group. Okay, so COO carboxylate, and in the case of sodium bicarbonate, you guys will form CO2 and water, and sodium, of course. And here the same thing. So here for carbonate, you also form the same products. Okay, so you are and actually this one is a better way how to do the neutralization, because you form carbon dioxide. Carbon dioxide is a gas, so you will actually see the neutralization with the bubbling. So this one is like a visual, right? A visual confirmation that you are neutralizing your carboxylic acid, is that you see the bubbling. In sodium hydroxide, you don't see the bubbling. So the other compound that is acidic that we have, learned in this class so far are phenols. Phenols are also acidic. So in the case of phenol, you have to be very careful. So let's say that you have a mixture of phenol and carboxylic acid. So if I add sodium bicarbonate, sodium bicarbonate is a weak base. So sodium bicarbonate, because of the differences in pKa between the pKa, right? Remember, guys, pKa from Gen Chem. The difference in pKa between the phenols and the carboxylic acids, the phenol will not react with the sodium bicarbonate. Why? Because this is too weak. This one is a weak acid. So weak acid, you need a stronger base. But this guy is not that strong to make it, get deprotonated, to deprotonate phenol. So in the sense of, let's say that if you guys have in a separatory funnel, you guys have phenol, and you have the carboxylic acid, right? If you add sodium bicarbonate, and of course, if you add ether, right? Let's say to do an extraction, right? You guys will have 2 layers. Let's make it bigger. You guys will have the organic layer, and you have the aqueous layer. Who is going to be in the organic layer? Well, the bicarbonate is able to deprotonate the carboxylic acid, but not the phenol. So the phenol will stay in the organic layer. Why? Because phenol is mostly hydrophobic. I know that we learned when we were doing the lab for phenol, phenol was actually soluble in water, right? But if you give the option to phenol to decide whether to go to the aqueous layer or organic layer, phenol will always go to the organic layer. Why? Because phenol is mostly carbon, right? It's like a huge benzene ring compared to the OH. So the phenol will prefer to go to the aqueous, sorry, to the organic layer. What happens with the carboxylic acid? Since the carboxylic acid gets deprotonated with the bicarbonate, you guys will have the carboxylate. The carboxylate is soluble in water. So that's how you can separate a phenol from a carboxylic acid. Now they are in separate layers. If you drain them, right, you guys can have your organic layer and you guys will have your aqueous layer. In the organic layer, you will have the phenol. And in the aqueous layer, you will have the carboxylate. So they are separated. So you can use the acid-base properties, right, of these two acidic functional groups and with the appropriate base. What if I instead of bicarbonate, I use by accident sodium hydroxide? Yeah, you use sodium hydroxide, you're in trouble. Why? Because sodium hydroxide is able to deprotonate the carboxylic acid and also the phenol. So they would both go to the aqueous layer. You don't want that. You want to separate them. So that's why you have to selectively choose one appropriate base according to the pKa values of both compounds. Okay, so that's just to to close a little bit on the acid-base properties of acid and bases of carboxylic acid. Benzoic acid is the representative for the aromatic acids, right? Benzoic acid is used in a lot of for a lot of applications, drugs. It's used as a preservative. If you look at your soda, whenever you guys drink soda, check the contents. You guys should find benzoate, sodium benzoate as a preservative. Let me see if I can find it here. The ingredients. Yeah, I have it right here. Right? You go to hopefully focuses here. Sodium benzoate is right there. Sodium citrate, citric acid is another acid, right? It's high fructose. Yeah, that's the poison of the soda. Citric acid, sodium citrate, that's a buffer. And then, of course, the citric acid and is an acidic. That's why it's so sour. The drink. It's only that if high fructose lowers that that sour taste. Okay, but you see sodium benzoate. That's coming from benzoic acid. Right. Later, I'm gonna drink this spray. All right, great. So let's go back to the slides. It's a relatively long chapter, but it's mostly, passing slides because it's about all the reactions that we have to learn. All right, so now, why the big question is like, why is carboxylic acid so acidic, right? So we have alcohols, but they are not that acidic, right? If you ask me like, okay, what makes the carboxylic acid, right, so acidic? So if you tell me like, why is this, right? According to the Ario, right, they're both attached to an oxygen. So what makes it so acidic? Always analyze the conjugate base. Whenever you address acidity, is by the conjugate base. So your conjugate base after the protonation, you can see that this particular carboxylate can be stabilized by resonance. So you have some resonance stabilization in carboxylic acid. That resonance is not observing alcohols. That makes this compound more acidic, right, than the alcohols. The alcohols are actually not that acidic. You need very strong bases to deprotonate a carboxylic acid. Okay, so that's translated in the acid-base properties. Yeah, you can use hydroxide, and then the carboxylate is resonance stabilized. That's what really brings down the acidity, right? Sorry, it brings down the pKa, making it more acidic. So the acidity can also be tuned, right? If you want to make more acidic carboxylic acids, you can use not only resonance, but you can also use induction. Induction in the sense of having electronegative groups. So here is a clear example of chlorinated carboxylic acid. So this one is acetic acid. This one will be chloroacetic acid, dichloroacetic acid, trichloroacetic acid. And you can see how the pKa decreases, meaning that the acidity increases. I don't know if it's like a linear relationship, it's a linear correlation, but you can see how the first addition drops the pKa by a lot, almost 2, right? 2 units. Then next is about 1 unit and a little more, and then it's about 0.4. Yeah, it's not that linear, but every chlorine definitely will add some electronegativity. This electronegativity will deprotect or will act as an electro-withdrawing group. That electro-withdrawing group will increase the polarity of this carbon. That polarity, right, that delta plus that is increased in this COO will ask or will demand this oxygen to steal more electron density from the OH, meaning the OH will be easier to get lost. Okay, so in this trichloro, TCA, trichloro should be TCA. Well, TCA, we call it transdynamic acid, right? This one is trichloroacetic acid. Yeah, the abbreviation should also be TCA. Okay, there is another one which is TFA. When I was back in graduate school, we were working a lot with TFA. TFA is trifluoroacetic acid. Imagine like replacing chlorine with fluorine. Fluorine is our most electronegative group. So therefore, the pKa of trifluoroacetic acid is going to be way lower than this. Why? Because you have 3 fluorines. If having 3 chlorines, the pK is already 0.9, you can more or less guess. It was so strong that as soon as you were opening the bottle of TFA, of trifluoroacetic acid, you will see the smoke coming out. So it was really, 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 acidic, let's call it like that. I could also even say that it behaves as hydrochloric acid when you open the bottle. Unfortunately, one of the graduate students, I remember from previous cohorts of students back then, he got that really bad burn from TFA. So be very careful if you run into the TFA, because TFA can also be very, very dangerous. What is the TFA used for in labs? It's normally used as a solvent. It gives you that acidity, strong acidity, small amounts, but big acidity when you are making a buffer, or to denature proteins. I was working with proteins back in graduate school, so we had to denature. Denaturing proteins means to unfold it, right? So you guys know that proteins have a particular unfolding, have a particular way how they can form helices or beta sheets, beta strands. So we were able to denature those structures, right? Secondary structure of proteins by adding TFA. TFA, by the acidity properties, was able to denature the protein. All right, so let's go now. Synthesis of carboxylic acid. So some synthesis of carboxylic acid that we have studied in the past are shown in this particular slide. You can see it on table 21.1. Some of them include the ozonolysis. The ozonolysis means that you will have like a cleavage, oxidative cleavage of alkynes. Alkynes only. Remember that for alkenes, you don't get carboxylic acid. For alkenes, you guys get ketones and or aldehydes, right? But if you guys have an alkyne, yeah, the alkyne oxygen in water, it will break this in half, right? It will split the alkyne in 2, and then each will be a carboxylic acid. That's in the case that you guys have an internal alkyne. Sometimes you guys have a terminal alkyne. If you have a terminal alkyne, don't forget that final, right? So let's say this alkyne, right? This alkyne, if you guys treat it with oxygen in water, you guys will cleave the alkyne. This one, the carbon base would be kept as a carboxylic acid, 1, 2, 3, 4, 1, 2, 3, 4. The number 4 will be a carboxylic acid, but that last carbon will be eliminated as a CO2, okay? So that's the only difference between an internal alkyne and a terminal alkyne. The terminal alkyne will get decarboxylated. I mean, you will lose that particular carbon, right, as CO2. Another way how to make carboxylic acid that we learned was in the primary alcohols, right? Oxidation of primary alcohol. You have a primary alcohol with sodium dichromate, sulfuric acid, and water. You guys will get the carboxylic acid. In this case, you retain the number of carbons. Here, no. You are decreasing the number of carbons, so be very careful when you use this or when you use this particular reaction. And in the last one, we learned it on chapter 16, aromaticity. 17, right? Aromaticity, chapter 17. On chapter 17, we were learning like side chains. As long as you guys have a benzylic hydrogen, that benzylic hydrogen can get oxidized to carboxylic acid. For example, this one is isopropyl benzene. This is an sp3 carbon. Sp3 carbons with a hydrogen, they can get oxidized to carboxylic acid, regardless of the nature, the size, the bulkiness of the rest of the side chain, right? As long as you guys have one carbon H, that's enough to do the oxidation and get a carboxylic group. Okay, another way, these are new ways how to make carboxylic acid. We kind of did this in the previous chapter, aldehydes and ketones. I don't know, you guys recall that from cyanohydrin, right? When we were doing cyanohydrin reactions, you guys will introduce in the cyano group to the aldehyde or ketone, and then you will hydrolyze in it to get carboxylic acid, right? So in this case, yeah, so that will, let me open my camera. So you recall, let's say butanone HCN, right? You guys were getting this compound, okay? Cyanohydrin. Then this cyanohydrin in H3O plus and heat, that was hydrolysis. These are the conditions of hydrolysis, by the way. H3O plus and heat. And then this one will get broken off, right? BOH, that's good. And then this one now becomes a carboxylic acid, whereas the nitrogen will become ammonium ion, right? Ammonium ion. Technically, it should be NH3, ammonia. But since you are in acidic conditions, the ammonia gets protonated, giving you ammonium ions. Okay, we don't need to know the mechanism. Yeah, that's the good news that I was telling you before. So, but that's an additional way how to make a carboxylic acid. So no mechanism for this. Okay, but we need to know it. Another one that's very important, maybe this one, I will show you the mechanism because it's kind of fun. This one is called the Grignard carboxylation. If you have, you need to make a carboxylic acid, you can use any Grignard reagent like this one, right? Can I use organolithium, Professor? You taught us in the Wittig reaction that organolithiums, they behave similarly, right? In a very similar style as Grignard. Can I also use organolithium? Yes, you can also use organolithium for this reaction. It adds, you gain one extra carbon. That extra carbon that you are gaining is the carbon from the CO2. I'll show you how it happens, this mechanism. That would be good for you guys to know. It's called the Grignard carboxylation. Okay, let's do propyl Grignard. Okay, so propyl Grignard with carbon dioxide. If you recall the structure of carbon dioxide is CO linear, right? It's an sp hybridization. Okay, so what happened with the Grignard, as we know, the Grignard can be also treated as MgBr plus and CH2 minus. So here, although carbon dioxide has a dipole moment of 0, but you guys have a delta plus, delta minus, right? So you can have some polarities distributed. So the C minus will attack the carbon. The carbon will push one of the oxygens, one of the pi bonds towards the oxygen. So what you guys will do, what we'll have is CH2, 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 C double O minus. You see how you're adding, right? 1, 2, 3, and then 4. 1, 2, 3, 4. This one is what it used to be as CO2. And then in a second step, right, as the reaction mentioned, you guys will have H3O plus, which is the protonation of the carboxylic group. and water, of course. Okay? And forming butanoic acid. Oh, about the naming, the ending is oic acid. So it would be methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid, hexanoic, heptanoic, octanoic, uh, nonanoic, right? And then, yeah, and then carboxyl groups, they will always have the priority, will always be terminal, same as the aldehydes. So they will always be at the very, top of the list in terms of priorities. Okay, so pentanoic, hexanoic, cyclohexanoic, cyclopentanoic, and benzoic would be your the aromatic version of the carboxylic acid, right? How are we doing so far? Hopefully we're doing okay. Okay, so that was for ways to prepare carboxylic acid. Now let's see reactions of carboxylic acid. For reaction of carboxylic acid, we will have the first one, which is reduction. We will reduce carboxylic acid. And then we'll kind of learn this reaction already on chapter 13 or 12 about alcohols, right? With alcohols, we learned chapter 12. We learned how to make alcohol was from the reduction of carboxylic acid. So you have any carboxylic acid, no matter what type of carboxylic acid, you will treat with LAH followed by acid, right? Acid or water, and you guys will get a primary alcohol, always a primary alcohol. The mechanism, you guys learned it before, right, on chapter 12, so you guys will not be asked the mechanism this time, right? So no mechanism for this. Okay? So maybe I will put a next. Let me write something. Okay, so no mechanism for this. What about for this one? For this one, yeah, you guys need to know the mechanism. Mechanism for this, no mechanism for this reaction. Okay. You can also reduce carboxylic acid with borane. This guy is called borane. I don't know if I can write it here without those lines, those streaks. Borane. It's so difficult to write with a mouse. Okay, borane. B-O-R-A-N-E. And THF. THF is the solvent because borane is a gas. So it's a gas that is dissolved in THF, which is a liquid, tetrahydrofurane, right? So those two is a reducing agent, and you also get a primary alcohol. So it would be exactly the same as the LAH. Mechanism for this? No, you don't need to know this reaction. Okay, no, you need to know the reaction, but you don't need to know the mechanism. That's what I mean. Okay, that's it about carboxylic acid. How do you guys like carboxylic acid? Very short, right? So there's not much to do or say about carboxylic acid. But what comes next is really what will involve like 80% of our time from now on, okay? So all these compounds, they all derive from carboxylic acids. I will write or draw carboxylic acid on top, right? Carboxylic acid is kind of the mother of all those functional groups. And you can see how they have that particular region in common. Right? So here, 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 they're all in black, right? So the only thing that you are doing to carboxylic acid is just substitute this region that is in green, or sorry, in blue, in light blue. So the chlorine makes it a halide. This is one is called the acyl. No, that's not acyl. The ester is kind of like an ester. Yeah, they will make it an anhydride. The ether will make it an ester, and the amino will make it an amide. Okay, so those are all the 4 derivatives that we're going to learn from carboxylic acid. So carboxylic acid is the mother of these 4 kits: halides, anhydrides, esters, and amides. And as any, I don't know, some of you might have 3 brothers or 3 siblings, right? So you might guys will definitely know this particular kid. For example, in my case, Abel is the most hyper of the siblings. Okay, so that hyper is the halide. Halide is the most stable. And also in the family, you guys will have the one that is the most quiet of the kids. So that most quiet will be the amides, will be the most stable, the ones that does not react, that does not do anything, and unless you put it with heat or with very reactive chemicals. Okay, so we have both sides, the very reactive and the least reactive. So the reactivity goes from left to right. meaning that the halides are the most reactive. Then we have the anhydrides, then the esters, and then finally the amides. But they all come from carboxylic acid. So if you guys want to make anhydrides, you can make it from carboxylic acid. If you want to make esters, you can make it from carboxylic acid. And you want to make amides, you will have to make it from carboxylic acid. Now, can these siblings also interact? Yes, you can. So, and then for that, you guys have this ranking of stability or reactivity. And then the most reactive is acid halide, right? So this one, acid halide. Now, how do I make an anhydride? The anhydride can be made from carboxylic acid. Well, they can all be made from carboxylic acid, but anhydrides can also be made from acid halides. Can I make anhydride from ester? No, you can't. You can only make something from one functional group for another functional group that is more reactive, right? So for example, amide is too stable. The amide is not going to go from high stability to less stability. No. You will always go from less stability to more stability. That's why the acid halide will get promoted, let's call it like that. Will get promoted to an anhydride. Why? Because anhydrides are more stable than acid halides. What if I want to make an ester? Well, if you want to make an ester, right? If you want to make an ester, then the ester can be made from anhydrides, but can also be made for halides. Why? Because ester is more stable than both of them. Carboxylic acid, of course, because carboxylic acid, as we said, carboxylic acid is the mother of all these guys. And the last one, if I have an amide, right? The amide can be made from esters, can be made from anhydride, and can also be made from halides. Okay, so that's the sequence. So that means that for halides, you're going to have a lot of reactions, maybe a little bit less for the anhydrides, less for esters, and way less for amides. Right? Why less for amides? Because they are the most stable. Of course, they don't have that many reactions. Okay, so are you guys ready for, well, that is the amide, the most stable, and the stability of the amide, really? I mean, if you guys want to find out, right? Because you would say like, Professor, why are amides so stable? Well, first is that all the reactions that we will do today, they will involve the polarity, right? As you can predict it, you guys will depend on the polarity of the COO. The COO is really the key part of this functional group. So the COO, so the more delta plus it is, the better, the more reactive. So for example, if you see the ester, right? Here the ester has some partial electron donating properties. So if the halide here is not that efficient, in the chloride, the halide does not really donate that much electrons. It can do, but like a very little, right? Compared to the oxygen can do it better. So between the chlorine, it will be a delta plus, whereas in an ester will be way smaller. In an amide, it's even less. Even smaller, medium, way more. So this is why the halides are more reactive than the esters, and the esters are more reactive than the amides. It's because of the delta plus. And why is the delta plus so tiny here? It's very tiny because in the amides, that nitrogen donates electrons to the carbon by resonance. There's a stabilization. So in the case, the nitrogen kind of shares the delta plus character of the carbon, right? So here you have a delta plus. So by the resonance, the nitrogen takes some of that stress from the carbon. So the carbon is not a delta plus. Now it becomes more neutral because now it's not, right? It's COO. Right? So this is why. In the case of the halide, no, we don't have that situation. Here, actually, the chlorine actually steals more electron density from the carbon, making it even more delta plus, right? The delta plus is even increased in the halides. Okay? Clear. Thus, the amide is also planar. right? So here, these groups, they work as a living group. That's why in this particular chapter, we're gonna be mostly learning substitution reaction. Because remember, for substitution reaction, you guys need a living group. Without a living group, we cannot have a substitution. So that's the purpose of that particular group. So what are gonna be the living groups here? The living groups are shared or are shown here. Excuse me. This one is the living group, this one will be the living group, this one is the living group, and this one is the living in red. Okay, so that's where you guys will see right? So they will serve as living groups, right? So let's see the next slide. Yeah, so that means that they will undergo a nucleophilic substitution reaction, and this one is the general reaction for this substitution. So we will have that the nucleophile, whichever is the nucleophile, will attack the carbon. The carbon will have to adopt that particular tetravalent. Tetravalent means that it will have four bonds, right? It has to form this intermediate, and then this intermediate will reject, or it will lose that living group. Okay, so the living group has to be lost. You cannot do that concerted reaction. It's not like an SN2. You cannot just attack and then lose the living group right after that. No, it has to push up, right? It pushes up those electrons, pushes those electrons up, and then they will come back down. And then as they come back down, then they will lose that living group, getting your substituted product. That's not the same in aldehydes and ketones. Aldehydes and ketones, they undergo addition reactions because they don't have a living group. In our case, we have those living groups, the ones that were highlighted in red. So that's really what makes the difference between aldehydes and ketones and these carboxylic acid derivatives. Okay, so this one is one example, right? For example, how to make an ester from acid halide. So I will show you the mechanism. My bad. Okay, so I really, for example, if I have a bromide, let's make it as a bromide. The bromide, if I attack it with methanol or methoxide, the methoxide will attack the carbon. The carbon now pushes those electrons towards the oxygen. You have the tetravalent intermediate. You have to show it, guys. Please don't skip it. That's the tetravalent intermediate. After that, of the tetravalent intermediate, this one will come back down, and then that's when I lose the bromine. And I form an ester. See? Depends on what is your nucleophile, you can form the other functional groups. Remember, in one case is the ester, meaning that you are making an alkoxide. For esters, you have to use an alkoxide. For amides or amides, some people, they call it amide or amide, you guys will have to use an amine, right? For anhydride, you have to use a carboxylate. Right? That's the one that does the attack. That's the nucleophile that is used for that. Nitriles are also a functional group that derive from carboxylic acid, but those are kind of like secondary derivatives. So that's why they are not. We will touch nitriles a little bit towards the end of this chapter, but nitriles also can come from carboxylic acids. Okay, they can be made from carboxylic acid, and they also can be converted into carboxylic acid by for different reactions. But that's the idea for mechanism. Okay, so that's a general reaction. For example, ester formation from an acid halide, in this case acid bromides, right? So bromide attacked up, down, out. So that's really the methodology how these reactions proceed, for not only for this reaction, for all of them. Right? So here you have the second step of this substitution reaction is the elimination, right? The elimination of so we will call this addition elimination. Here first you have addition, and second you guys have elimination. Okay? It's not an SN2 reaction. Be very careful. Do not do an arrow like this. It's not an SN2. You cannot just attack and then kick out. No, you cannot do that because it's not an SN2. This one, as you show it like that in this current slide, so that is showing an SN2 reaction, and this is not SN2. Hydrolysis, yeah, this is the ester hydrolysis. So for hydrolysis, actually, I will do the, yeah, I would say it's a reaction. This should come later, but it's a hydrolysis. We will see it mostly for esters. I mean, really, any of those groups can be hydrolyzed. The acid halides, the acetic anhydrides, sorry, anhydrides, esters, and amides. So, okay, so remember, maybe I will show it better here. Okay, so we say that carboxylic acid, right, is the mother of all those compounds, the halides, the anhydride, the esters, and the amides, right? So those are the four groups. So the amide is the mother of those, right? But these guys can also go back to the carboxylic acid by doing hydrolysis. Always. They do hydrolysis. This hydrolysis will always involve the use of water and is acid or base catalyzed. You can use it in acid, H3O plus, or base in OH. The most commonly used, to be honest, is acid, but they can be both, they can be done in both conditions, acid or bases. So we can do the mechanism for, for either the acid or the base, but what is the difference between, are all the hydrolysis the same? Well, some hydrolysis are easier, right? Remember that acid halides are more reactive. So maybe the acid halide hydrolysis does not require heat. The anhydride are also reactive. Maybe the hydrolysis, this one does not require heat. Esters are more stable. Therefore, the hydrolysis, this one might need heat. And amides, of course, they are the most stable. You might even need reflux, boiling, catalyst, etc., etc. So you need, for the amide to do a more rigorous degradation or hydrolysis. So amides, for example, is proteins, right? So anytime that you guys want to degrade protein, you have to cook it, right? So the cooking for us, I mean, the kitchen, what we do is we denature the protein, but for us to make it easier to digest. But really, you are also hydrolyzing the protein. The protein is getting hydrolyzed to get carboxylic acid and amines, which is what we call the amino acids. So all that meat, chicken, fish, lamb or beef, they're all being hydrolyzed. When you cook them, you hydrolyze them. So they get hydrolyzed. So when they go to your stomach, it's easier for the pepsin, right, which is an enzyme that is in your stomach. It's easier for the pepsin to degrade the meat, right? The same thing happens with the vegetable, but vegetables are more glucose, carbohydrates based and fibers. But in the case of meat, protein, yeah, you need to get your amino acids. So the only way how to get the amino acid from the protein is by hydrolysis. Okay, so the hydrolysis will occur to all this. On the slides is showing you the hydrolysis of ester. That's what it was showing you. I will do the mechanism for that. In the case of ester, it's kind of special because it is an ester. I mean, I will use a formal carboxylic acid, okay? So carboxylic acid, okay, butanoic acid. And then we will have an alcohol. Let's do isopropanol in H3O plus, right? And water. Yeah, well, it's already involving water. Yeah, water. So this one it will produce an ester and water. Okay? So this reaction is a ester formation. So this way is called esterification, right? So esterification is this way, and the opposite way would be hydrolysis. Is this reaction reversible? Yes, it is reversible. And they're all reversible. This one, all the hydrolysis and formation, they are all reversible. So the only difference is depends on how you want to do it. For example, here, for the esterification, you always need catalytic amounts of the acid. And to do the reverse reaction, you will need concentrated, acid for that. Okay, you need more acid to do hydrolysis and less acid to do the forward reaction. Now, for the esters, since it's so popular to make esters, they call it the Fischer esterification. Let me check it out for a minute. It is with a SC, Fischer, because that's the one that always debated between the. I'll have to double check. I will get back to you on that. That name is Fischer with CH, or is Fischer as fish, right? Like, okay. So it can go both ways. Oh yeah, it's correct. Yeah, it's Fischer with SC. This one is the correct spelling. Okay, Fischer esterification. And let's do this is already the only mechanism that we're going to do. Okay, so let's do the esterification. Okay, so let's do the carboxylic acid is exposed to H3O plus. Remember what happened in the previous chapter 19? We had to protonate, right? The protonation occurs from this C double O. C double O gets protonated. Okay. And now comes what? Comes the nucleophile. The nucleophile is isopropanol. Isopropanol adds to the, right? Adds to the carbonyl from the carboxyl group. Okay, so I have this particular compound, right? So the OH is there, the other OH, and the isopropanol adds. Now this isopropanol, according to my reaction, I should lose one oxygen. So I have to lose the OH. How do you guys lose OHs? By protonating, right? So here I will first deprotonate it with water because the H3O plus comes with water. The water can deprotonate that H. You guys get a neutral. Isopropanol, right? And I need to lose that OH or this OH, it doesn't matter. So I will do another protonation. Okay. Now this is a good leaving group, right? Because now it's protonated. So who is gonna help me to lose that? Well, you have to bring electrons down. So this one will come down and this one get lost. That's where the substitution occurs. This is the Fischer esterification. Okay. And then I lose water. That water gets lost. I'll circle it so you guys can recognize what is the water that gets lost. And then this water helps me to deprotonate that extra hydrogen that I have right there. And you get your final product, right? Plus H3O plus, which is my catalyst, right? You get the ester. This one is the Fischer esterification. That's the forward reaction. And I don't know, you guys recall it from the previous chapter, chapter 19. If you guys want to do the reverse reaction, the mechanism is exactly the same. You just go backwards. If here the last step involves deprotonation, the first step for the reverse reaction will be protonation. If here the second to last step is the loss, is the water loss, then for the reverse reaction, it will be the water attack, right? If here is this step is the protonation, in the reverse reaction will be deprotonation. If this one is deprotonation, and the reverse will be protonation, right? So here is nucleophilic attack, then in the reverse reaction will be loss of leaving group, right? So everything will be exactly the same, except like, it's the opposite reaction. Okay, it's the opposite. You will reverse it if you are being asked the hydrolysis. Okay, so I'm just showing you the Fischer certification. Fischer certification is right this mechanism right here. So you guys can definitely come up with this hydrolysis, which is the opposite reaction. Definitely will be in any of the quiz, maybe not the quiz, but maybe on the exam will be this mechanism. All right. So that is the hydrolysis. That's the one that you guys have to do. Now you see what are the products for this particular hydrolysis reaction. Okay. So that's the first step, is the protonation of the COO for the hydrolysis. Here to hydrolyze it. Here you can also do produce an amine, sorry, an amide from the ester. So now in this case, the attack will be with the ammonia, because ammonia will be your nucleophile, right, to produce an amide. How do you know that it's an ammonia? Well, because you need to add a nitrogen, right? A nitrogen next to the COO. This one has to be lost. Okay, that's more of the hydrolysis. Okay, so this one is that I don't know what this is doing here. This one shouldn't really be here. My bad. Just ignore this slide. So that's the first step, protonation, right? And then you lose it to produce the methoxide. Yeah. Okay. It gets protonated. Yeah, that's the second step. Okay, protonation of the once it attacks the water. After that, the water attacks, then will be the protonation for you to lose the methanol, and then you get the carboxylic acid. Okay, now comes the consolidated of all the reactions. For here, for me, it's just clicking really. So we will not be doing any more mechanism. That's the only mechanism we have for this chapter, which is the hydrolysis and Fischer esterification. And I also taught you, right, the Grignard carboxylation. Those are the only mechanisms that we have for this particular chapter. All right, so we have here the acid halide. So the water in here, in this case, is HOH. The OH will be the nucleophile, the one that's going to replace the chlorine. So that's why you get that carboxylic acid. This is hydrolysis, right? If I change this the nucleophile to amino group, right? So you will have to use you will be producing an amide. Two equivalents. Why two equivalents? Because you need to deprotonate the NH3, right? Because at the end, the NH3 adds, right? But then you have to remove, because it will be NH3 plus. You need to add something to remove it. So that's why you guys need two equivalents. The second equivalent of the ammonia will be to make it neutralize the amide. Reduction of acid halides, you guys have with excess LAH, lithium aluminum hydride, followed by water, step 1 and step 2. It takes you to primary alcohol. Same as carboxylic acid. If you don't want to fully reduce it, because this one is a total reduction, you are fully reducing the acid halide to primary alcohol, but you can also stop at aldehyde. If you want to stop at aldehyde, what you guys have to do is you have to poison this or make it less available, the hydrides for the reducing agent. So you have to make the reducing agent weaker. How do you do that? So instead of using LAH, remember, is aluminum with 4 hydrogen, with 4 hydrides. I hate those lines. I don't. Okay. This is aluminum, Al. So here, instead of making 4 high hydrides available in LAH, what they do here, they replace each of those with these terbutoxides. Okay, so lithium triterbutoxide aluminum hydride. Instead of having lithium aluminum hydride, right? Because LAH is lithium aluminum hydride, they make it weaker with a lithium triterbutoxy aluminum hydride. Okay, so then if you use that reagent, now instead of having a primary alcohol, what you guys will make is an aldehyde. Make sense? Step 1, step 2. So that one gives you a partial reduction, lithium triterbutoxy aluminum hydride. If you use LAH, it takes you directly to second primary alcohol. But if you use lithium aluminum triterbutoxy hydride, it will take you to aldehyde. Grignard reagent. Grignard adds twice to the acid halides. Right? Twice. You see, it gives you alcohol, but then you get twice the Grignard. This R is added twice. Once again, we are not doing the mechanism. It's all memorization. I'm sorry, guys. Yeah, we have to memorize all these reactions. So excess Grignard will give you two, right? Two Grignard addition giving you alcohol. It's how to make tertiary alcohols, really. It's step 1 followed by step 2. Now, what if I don't want to add 2 Grignards? I want to add only 1 Grignard. Okay, if you don't want to add only one Grignard or one alkyl group, then you cannot use Grignard. Grignard is too aggressive. You have to use one nucleophile that is not as efficient, is not as aggressive as Grignard. Who is that nucleophile that is not as aggressive? Cuprates. Lithium dialkyl group cuprates is the same as the Grignard, but instead of magnesium, it has copper. So here you guys have 2 groups, right? Let's say methyl. It will be lithium dimethyl cuprate. So the cuprates will add only once. Right? So you guys have an acid halide with methyl dimethyl cuprate, it will give you only 1 methyl and will stop at ketone. Okay, remember in Grignard, you were adding 2 Grignards. Grignard adds twice and leads you to an alcohol. The cuprate, no. The cuprate only adds once and stays as a ketone. Okay. Any questions? Anything that you guys might want to ask? Remember that you guys can send me an email, right? Or the screenshot, or or ask me during lab hours or during office hours. This one is a condensed slide with all the reactions. Can you use that during the exams or tests? No. I mean, for the in-person test. I mean, if it's online, there is no way I can prevent you from using it. But if it's in person, yeah, you guys cannot use it. Okay? Good. All right. So another reaction that I didn't really go over is this reaction. Very important. How to make acid halides. Acid halides can be made from carboxylic acid and SOCl2. SOCl2 will convert this into a Cl. A similar reaction is the one that involves PBr3. Okay, so let's say that I have this. I have benzoic acid. I use SOCl2 in pyridine, right? PY is pyridine. So it will convert it to like this benzyl chloride. Okay, so here, can I get the bromine version of that? Yeah, of course, you can get the version. So you have benzoic acid, and now instead of SOCl2, you guys will use PBr3. PBr3 will convert the benzoic acid into the bromine derivative. Right? So you have both bromine, right? The bromine and the chlorine versions. Okay, so once again, this slide, that would be, I would say this one is going to be one of your best friends, this slide, because it has all the reactions that we just studied. There's many of them. Okay, so this one is the ester formation, amine formation, amide, the primary amide and the secondary amide, depending on the type of amine that you are using, primary amine, secondary amine, or ammonia. This one is an amide, primary amide, secondary amide. So we here reduction, full reduction with LAH takes you to primary alcohol. partial reduction with lithium, titrybutoxy, aluminum hydride, it takes you to aldehyde. Grignard, if you do with Grignard adds twice, taking you to an alcohol. Cuprates add once and stops at ketone. Okay, you don't get an alcohol with cuprate. Good. Now, let's go to anhydrides. We're in the second functional group. Right? Remember, as I told you, like as we go down the stability, I mean, it will get more stable. The number of reactions are smaller. Okay, so ways how to make anhydrides. The best way how to make anhydride, of course, symmetrical anhydrides, is by with a thermal formation. Carboxylic acid at 800 Celsius degrees, really hot, right? Maybe even in the gas phase. In the gas phase, they will merge, condensate, forming an anhydride. Okay, what is that word condensation? Now that I just used it. Every time that you see you are condensing something, you always lose water. Okay? Anytime. So like, oh, that reaction is the condensation of, to form an ester. Okay. Ester condensation means that you're forming water. So water is one of the side products. That is what condensation means. Okay, so the anhydride is coming from that. So another example for condensation, for anhydride is, for example, if I have two carboxyl groups adjacent, right? Two adjacent carboxyl groups. Remember, intramolecular reactions are favored. So if I use 800 Celsius degrees, of course, these two will condense and you guys will form an anhydride. Okay, that's an anhydride you guys will form. Professor, can we make a anhydride with two different carboxylic acids? Yes, you can do it, but it will not be that clean because you will form a different sets. You will form an anhydride, cross anhydride, self anhydride, and self anhydride. So you will form a total of 3 anhydrides. Anhydride between these two. Yeah. 1, 2, 3, 4. 1, 2, 3, 4. Good. The self anhydride, this with itself, and the other self anhydride, this one with itself. It's not the cleanest way how to make anhydrides if you want asymmetrical anhydrides. If you want asymmetrical anhydrides, there is another way how to make it. Once again, we don't need to know the mechanism, although you guys can. I mean, you should be able to, but I'm not going to ask you, but it's just a substitution reaction, right? It's the azole substitution reaction. The other way, if you want an asymmetrical anhydride, what you guys have to use is, for example, I want to make this anhydride, right? This one. So you guys have to use one acyl halide, right? Let's say like this one is going to be my acyl halide, and this one will be my carboxylate. So acyl halide, I will mix it with the carboxylate. So acyl halide and carboxylate, it will give me the mix anhydride. Now this one is pure. This one is clean. Because I'm making attack, right? I'm attacking the halide with the carboxylate. Okay, and then you get this product. Don't do it through this way, through thermal. The thermal is only used for symmetrical anhydrides. If you want like a asymmetrical anhydride, then you will have to use this technique, the acid halide and the carboxylate, right? That's the one, right? That's the one that you guys see in this slide. Is the reaction of an acid halide that is for non-symmetrical anhydrides. Good. These are the good living groups. The two good living groups that are in those two reactive acid derivatives, right? Now, to be honest, the differences in stabilities are very similar. I mean, the acid halides are less stable, right? than the anhydrides. These are more reactive. The acid the acid halides are more reactive, but really by very little. So it's not like, oh, this one is way more reactive. No, they're about the same. So actually, in our reaction in the lab, you guys are going to be making acetaminophen, if I'm not mistaken. You guys will make acetaminophen or Tylenol, and you guys will use anhydride, because the anhydrides can be are slightly more stable and they can be stored at room temperature. The acid halides, no. The acid halides are more reactive, and they even react with the moisture of the air. Okay, moisture of air can even do the hydrolysis under at room temperature. So if you guys are working with acid halides, they have to be kept in the freezer, right? So they have to be kept under controlled pressure and temperature, because they are very reactive. Okay, but in terms of reactivity with a nucleophile, they have about the same response. Okay, the same reactions that you guys were doing with acid halides, they will also be done with anhydrides. So here are some examples for, so the lithium triterbutoxy aluminum hydride, the amide formation, the reduction, the Grignard, the cuprate, right? The formation, the ester, the amide, the amide, the primary amide, the secondary amide, they're all the same as we studied for the previous case. Okay, all right, so let's do like a small, few examples. I'm gonna start writing, and then I need you guys to start answering these questions. Okay, so you guys will pause the video. Okay, as I'm writing, please just start solving. That's it. Right. Okay, definitely we can make way many more problems of this, but just leave it. Maybe I'll do one more. All right. Okay. So, okay, ready? So I will pause it for each of these problems. Ta-da. Yeah. 7 examples. All right. So let's get started, right? All right. So we have first carboxylic acid with PBr3. What happened with PBr3? Remember that the PBr3 changes that OH into bromine. So I will have the same carbon skeleton, but now instead of carboxylic acid, I will have a acid bromide. That's after this. Now here I have a combo, LAH and acid, right? So LAH reduces, right? totally the acid halide to a primary alcohol, right? So it will be 1, 2, 3, 4, 4 carbons in an alcohol. 1, 2, 3, 4, alcohol, primary alcohol. Good. If you're not sure, please just check those slides, right? That's the ones that I was showing it to you right now. Where are we? Where are we? Where are we? Right here. That's the reduction, right? Acid chloride or acid bromide with LAH, excess LAH. You guys have a primary alcohol. Once again, Professor, how do you know all that? Because yeah, it's by repeating it. In my case, 12 years teaching this class. So, and then adding more. I mean, maybe by the time I'm teaching you this class, maybe it will be 13, 14, 15, 20, hopefully no more than 20 more. And I'll see how many more semesters I can be around, guys, right? It'd be good for you guys to once in a while, like send me an email. My email address is always available online, on BNCC, and send me an email to tell me, how you guys are doing in the STEM, right? In STEM or medical school, I always have a close relationship with my former undergrad and grad professors. It's always good to talk to, professional things once in a while. All right, so let's go back. So carboxylic acid and catalytic amounts of acid and alcohol. Okay, this one, alcohol with carboxylic acid, is the Fischer esterification. Alcohol in catalytic amounts of acid. So you form an ester. The OH is lost, and then instead you are putting the alcohol. 3, right? 1, 2, 3, 1, 2, 3. Done. Good. Here, excess ethyl Grignard. Grignard always adds twice. Okay, so in this case, I will have 1, 2, 3, 4, 1, 2, 3, 4, and then I know that Grignard adds twice. Okay, ethyl. I'm adding twice, and then what happens with this oxygen? Becomes alcohol, OH. That's with Grignard, always twice. Cuprate is the one that adds but once. Okay, in this case, I have an anhydride. Okay, in the anhydride, remember the ester side is the one that is the leaving group. This one leaves. Here is easier, right? Because you make always the halogen leave, but in the case this is not. So this one is my skeleton. I will have 1, 2, 3, 1, 2, 3, right? Methyl cuprate adds once, methyl, and the rest is intact. So meaning that you have a double O ketone. Yeah. I'm forming butanone with this. Yeah, interesting. I'm gaining carbons here, right? So I'm making a ketone. Next. Okay, this one. Pause it if you need it so you guys can try it on your own first. Okay, so carboxylic acid at 800 Celsius degrees. That's the self-condensation to form an anhydride. So 1, 2, 3, 1, 2, 3, anhydride. Yeah, that's the anhydride. And after that, I have excess of secondary amine. So I'm making an amide. Right? Remember, this one is the leaving group. That's gone. This one is the one that's going to form the amide. That forms the amide, adds N with 2 wins, right? Dun, 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 dun. What happened with that nitrogen? Yeah, that nitrogen left because that's the one that got lost to form the amide. So that will be the product for this reaction. Good. Next one, acid bromide with carboxylate. That's how to make anhydrides. 1, 2, 3. Now comes the carboxylate. Yeah, that carboxylate has 2 carbons. 1, 2. Second step is lithium aluminum triterbutoxyhydride. That is the partial reduction, right? Partial reduction of the derivative, right? So this one is my leaving group. Done. This one, right? this one. I will partial reduce it, right? So partial reduction, full reduction will be alcohol. Partial reduction will be aldehyde. So this guy is going to be an aldehyde. That's the partial reduction. Okay? Aldehyde. That's your product. Professor, what is left of the lithium aluminum triterbutoxyhydride after the reaction? We don't care. What is left of the cuprate after the reaction? That's okay. We don't have to write it. What is the what is the side product after the Grignard? What happened with the MGBR? Don't worry. That one you guys don't have to write it. Okay. So the only thing that you're responsible for are the carbon, the carbon compounds, right? The organic compounds. Okay. Good. Great. So we are halfway of the chapter. A lot of reactions, as I told you, right? So let's see how we do with the next pool of so before we go to the next section, which is about ester, well, actually this one is the two last this is an example of synthesis, synthesis of compounds that actually reflect the two functional groups that we'll be covering now. So it is the ester, aspirin is an ester, and here Tylenol is an amide. Those are the two next functional groups that we will see. So the application for this reaction that we're about to study, really, they have really, real applications, right? In pharmaceuticals and in industrial compounds. Right? So Tylenol, I think this one is one that I like to do in organic chemistry 1. And this one is the one that we will do aspirin. If it's not aspirin, we will do, this is aspirin. So we'll do aspirin in the class, which is the ester formation. So we'll use an anhydride. So as I was telling you guys before, acid halides, even though they are more reactive, right? The reaction should be faster, but they are not that stable at room temperature. Anhydrides are more stable. So, and then they have about the same reactivity. So if there was stability and reactivity, even though those two concepts are connected, but we could even say that anhydrides and acid halides, they have the same reactivity, but the anhydrides are slightly more stable, right? So this one is the reactions. This one is the one that we call Fischer acidification. You see the carboxylic acid in methanol with catalytic amounts of acids. You guys can get esters and water. That's a condensation reaction. That reaction can also be done in basic conditions. But as you see, the basic conditions has to be followed by the acidic treatment. This one is the hydrolysis. Okay? So the hydrolysis is not the ester, but the same way. The acidification, Fischer acidification, can be done in acid and bases, and the hydrolysis can also be done in acid and bases. We will normally do the acidic one, but acids are also doable. So this one is the acidic hydrolysis. Now you see that the acid is not used in catalytic amounts. Now the acidic is used in reagents amounts. So stoichiometric, 1 mole, 1 mole. Here, no. Here is in catalytic amounts, very small concentrations. Okay? Esters, we are now with esters. Reduction of ester will take you with excess LAH. It will take you to primary alcohol and methanol. So here we will have a cleavage. Let me get a color. Okay. So you will cleave here. This one will form a primary alcohol, which is right here, and the methanol, which is the other side. So in this particular reaction, you guys need to declare, you need to state, you need to mention both alcohol products. So they are both going to be primary, they're going to be alcohols. We don't know yet if they're going to be primary, secondary, or tertiary, but there will be 2 alcohols. In this case, you guys cannot ignore the second alcohol. Okay, that's excess LAH. Can I use sodium borohydride? I also studied sodium borohydride. No, you cannot use sodium borohydride. Can I use lithium triterbutoxy aluminum hydride? No. Here right, we know that particular reducing agent, lithium triterbutoxy, is used for acid halides and anhydrides. For esters, we use a different one, which is called DIBA. DIBA is the abbreviation of diisobutyl aluminum hydride. Say it again, diisobutyl aluminum hydride. If you want to try faster, try faster. So that's how you will remember. So DIBA is a weaker reducing agent, same way as the triterbutoxy, but don't use triterbutoxy with esters. For triterbutoxy, for esters, you use diba. So one diba, second step, acid or water, and then the reduction will stop at aldehyde. And of course, don't forget that you will also get the alcohol, the methanol. So you guys have to state both. Please, in esters, you guys have to state both. Grignard also works with esters, and Grignard always adds twice. Okay, the only exception that Grignard doesn't add twice is in nitriles. Right, so that's coming next. But so far with acid halides, twice. With anhydrides, twice. With esters, twice. Okay, so Grignard will always add twice. Okay. So right now we already covered this, we're done with this, we're done with this. Okay, the most stable or least reactive is amide. So let's see what we have in amides. How do we make amides? Amides are made by mixing acid halides with two equivalents of ammonia, or amines or secondary amines. That they also can get hydrolyzed. We are not going to do the hydrolysis of amides, although you guys could. You shouldn't be surprised if I do, but you know, it's the same thing. You guys, no, I mean, I'm sure that you guys are tired of mechanisms. So I'm not going to do this mechanism. So the only mechanism that we will have for this, I will keep my promise. Yeah, I'm a good professor. I'm not going to add you in the middle of the chapter. So the only mechanisms is Fischer esterification, forward, and hydrolysis, right? The Fischer esterification and the hydrolysis of esters and the Grignard carboxylation. Yeah. Okay, let's leave it like that. I promise, I'm not adding anything else. Okay, so the amide can also be in acid and heat, can get hydrolyzed. You guys will hydrolyze right be in the middle of the amide. This one will be a carboxylic acid, and this one will be an ammonium ion. Technically, it should be NH3, but since NH3 in presence of acid is protonated, you guys will get NH4, okay? Always watch out for the acid environment. The acid environment will also condition the products. You have to protonate the acid in acidic conditions. You cannot have it deprotonated in acid, because in acid, anything can get protonated, okay? Amides can also get hydrolyzed in bases, okay? So sodium hydroxide and water, of course, and heat. You always need heat to hydrolyze. And then in a second step, you guys will add acid. Yeah, you also get carboxylic acid. What else, professor? You also get NH4. NH4 plus will also be another of the, the secondary product from this reaction. All right, good. Amides with excess LAH, what happens? Primary amines. You guys will get primary amines. Very similar reaction that you guys have with carboxylic acids, with amides, with acid halides. You guys will get a full reduction with excess LAH. In this case, it will not be an alcohol, it will be an amine. So an amine, a primary amine, will be obtained from amide. So this carbon is the one that becomes the CH2. That carbon in green is this carbon in green. So you don't gain, you don't shorten the chain, right? The length of the chain. So the chain of the length will be the same. Okay, so nitriles. How to make nitriles? Nitriles are made by SN2 reactions of alkyl halides. This is an alkyl halide. Now we are in nitriles. Nitrile is a subdivision. I know it's not an amide, but it's commonly seen here. Nitriles. All right. Nitriles can be synthesized by SN2 reaction. You have sodium cyanide, potassium cyanide, any cyanide really. Alkyl halide, it will be a nitrile group. That's how you make nitriles. The other way how you can make nitriles is from amides. Amides with SOCl2 will dehydrate it, giving you like a nitrile. You don't need to stay those two, so don't worry about those two. So you don't need to write it. Really, what we care about is the nitrile, and here this carbon is this carbon, okay? So don't add, don't subtract any carbon. So if this one is a CH3, your nitrile will be CH3 nitrile, CH3 nitrile. All right. Nitriles can also hydrolyze, but the hydrolysis of nitriles have two steps. Why? Because a nitrile is the dehydrated version of an amide, and the amide is the one that gets hydrolyzed. So the nitrile in acid and heat will hydrolyze to an amide, but the amide under the same experimental conditions will hydrolyze. So you guys will have to I mean, it's really it's time dependent. The longer that you leave it, of course, the full hydrolysis you guys will get. But nitriles they get hydrolyzed to amides, and then after amide, they will get hydrolyzed to carboxylic acid and ammonium ion. That hydrolysis can also occur in basic conditions, sodium hydroxide, followed by acid treatment. You guys will get your carboxylic acid. Of course, this carbon right here is this carbon right here. You are not adding, you are not subtracting carbons to these reactions. All right. So to be honest, the only one that you're adding carbons could be the cuprates. You're adding in Grignard. Yeah, that's the only one. Yeah, that's the only case that you're adding groups. Oh, and the Grignard carboxylation, right? Nitriles with Grignard. Yeah, that's the only exception. Remember I was telling you? Normally Grignard adds twice, but in nitriles, it only adds once. Okay? And you guys get a ketone. Okay? So Grignard with nitrile gives you ketones. But it has to be Grignard followed by acid. Even if I add excess Grignard, yes, even if you add excess Grignard, the reaction will stop at 1. Why? Because this one is a nitrile. Nitrile has a triple bond, so triple bond is way easier to degrade. So that's why not even the Grignard can destroy a triple bond that easily. Right? So at least in the COO is a double bond, so Grignard can work it around. But in the case of a triple bond, yeah, the Grignard cannot. I mean, Grignard is very nucleophilic, but not as nucleophilic to handle a triple bond. Right? So full reduction with LAH, excess LAH on nitrile will take you also to a primary amine, the same as the amide. And this one is a full condensed version of all the reactions we just studied. Okay, so we are almost done. I mean, definitely we will have some examples, some work problems, but basically, I mean, yeah, that's really the last slide for this chapter. This one has a condensed version of all the reactions we studied. Well, I will do the one for, acid halides and anhydrides separately, but pretty much you have everything in this slide. All right. Good, so let's do some examples. Maybe I will pause the video while I'm working, so I'm not really taking your time, right? So just take a water break. I'll be back with the problems for us to solve on esters, nitriles, and amides. Right, so here I came up with some problems. Please just take a screenshot or make a pause. Try to solve them. I have like some about 7 problems to do about esters, nitriles, and amides. Here's short view. Briefly, yeah, we're gonna solve all these problems. All right, so pause it and then try to solve them by yourself, and then we'll get together. I mean to do it. To give answer to these problems. All right, so let's start with the first one. So we have an ester right here. I can recognize the ester. I here have H3O plus and heat. H3O plus and heat is hydrolysis, correct? Yes, hydrolysis. The hydrolysis, I have to break the ester. One side will be the carboxylic acid, the other side is the alcohol. Technically, it should be 2 separate molecules, right? You divide, you split the molecule into 2. But since the ester is a lactone, that's the word for a cyclic ester is a lactone. A lactone, then you guys will get only one compound. So this side in red will be a carboxylic acid, or in blue. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this one will be in red, and that one carries the OH. Okay, so here will be the same compound has the acid and the carboxylic acid and the alcohol to make the ester, right? Good, great. So next one, acid halide with excess ammonia. That gives me amide, right? Great. Amide, right? The Cl gets substituted, the NH2 comes in. Now this amide is treated with SOCl2. That's the dehydration of the amide. Dehydration means I'm losing the water. So I will have a nitrile. This C in blue is this C in blue. I'm not gaining any carbon. So don't do 3 carbons and then nitrile. No, the carbon of the cyano, right? The cyano group is part of the chain because this carbon gets, converted into this carbon, then it's triple N. All right. And then make sure also that your nitrile is straight. This one is an sp hybridization. It is wrong. I will take points off if you guys bend the nitrile. The nitrile cannot be bent because it's an sp hybridization. Okay. Okay, so next one, alcohol, propanol, 1, 2, 3, propanol. In methanol, in catalytic amounts of acid. Okay, that's an ester formation. 3, ester. What is the alcohol? Methanol. Okay, so that would be the first step. After that, they give me diba. Okay, diba is the partial reduction, right? Remember, that's the one that stops at aldehyde. So I will cleave the alcohol. This alcohol has to be reported, has to be, part of the answer. So that's methanol. Plus the other side is an aldehyde. 1, 2, 3, aldehyde. 1, 2, 3, aldehyde. That will be your two products for this reaction. Good. Great. Next. 1, 2, 3, N-propyl bromide, right? N-propyl bromide with KCN, that's an SN2 reaction. The cyanide replaces the bromine. It's a conventional reaction from chapter 7A. The CN. Okay? 1, 2, 3, 1, 2, 3, CN. Now the CN is added. That means that you will have an extra carbon. Ethyl Grignard. Okay, in nitriles, Grignard only adds once. And then in acid cleaves it and then give me a ketone. Okay, and that carbon is the one, the keto carbon, right? The ketone carbon will be that. 1, 2, 3, double O, ethyl. This ethyl is this ethyl, by the way. Okay, so that ethyl is the one that I'm adding. This is 1, 2, 3, 1, 2, 3. This carbon is the carbon ketone, right? Acid halide with isopropanol. Okay, that's an ester formation. Acid halides with alcohols is esters. So the first step would be benzene ring ester. Okay, that's after step 1. Do I need acid as a catalyst? No, we don't need a catalyst because this function group is so reactive that it will spontaneously react. So it will not need any acid. Second step, that aldehyde excess LAH followed by acid. Okay, that's a total reduction. That means that I will get a primary alcohol. But before doing that, the ester has to be split, right? Cleaved. I will have this as an alcohol. And this guy will be fully reduced because it's LAH. Diba will give you partial, right? As we did here, partial to aldehyde. But now with LAH, it goes all the way to primary alcohol. So it would be benzylic alcohol right here. Good. Next one, carboxylic acid with excess ammonia in actually, you don't need the catalytic amounts in this case because ammonia will give you the basic environment. So after the ammonia, you guys will get the amide. And then after that is excess LAH. So it will reduce it. Basically, we'll get rid of this C double O. NH2. Okay. 1, 2, 3, 1, 2, 3, NH2. Okay. And the last one, NH2 with SOCl2, that's dehydration. 1, 2, 3. And then the third one is part of the nitrile. Okay. 1, 2, 3, 1, 2, 3. Methyl Grignard in acid. Okay. Methyl Grignard, remember the Grignard adds once with nitriles. And then stops a ketone, right? And then adds that methyl. Yeah, that methyl is this methyl. Good. Right, so let's just do a couple more. I didn't cover some of the other reactions. Let's say here I have excess ethyl Grignard followed by H3O plus. Okay, so I have here okay, that's how to form amides. Okay, so these are the last three examples, a little bit more elaborated. I have an ester here in excess Grignard. Remember that Grignard adds twice, always with the exception of the nitriles, right? In nitriles only adds once. So whenever you guys do a green esters, all esters will always cleave. So you guys will lose this one first. So that would be 1,2-ethanol. And to whatever is left, the Grignard will add twice. If you have a skeleton of 3 carbons, 1, 2, 3, 1, 2, 3, that blue carbon will add Grignard twice. Ethyl, ethyl. So what's done? What is left for the oxygen? Well, if it already has 3 bonds, the only is 1 bond available. So you guys will form a tertiary alcohol. Okay. Um, propylene hydride with excess amine. So the excess amine, primary amine, methylamine will substitute remember the carboxylate, the one that gets substituted. And then this one with the blue dot is the one that will add the amine, NHCH3. Okay. Do I have to write the side product of the living group for the hydride? It's organic. Yeah, I mean, I know it's organic, but it's a living group. So that living group in particular, we don't have to report it. Same as the living group for acid halides. I mean, we don't have to report. But I mean, if it helps you to keep track of what you are losing, yeah, that would be the living group, right? 1, 2, 3, oxygen. 1, 2, 3, oxygen. And the last one is called transamination. Transamination is the process of changing something into an amine. In this case, it's an ester that is taken to an amine. So this alcohol this ester will break. Okay. Where do we see that reaction? We saw that reaction right here. Right? Ester with amine, you guys will get the amine, the ester displaced. Okay. So in the case of the transamination, this one is lost methanol plus this one, 1, 2, 3. 1, 2, 3, the blue dot will be double O. And then what is added is the amine, NaCH3. Okay, so those will be the two reactions. Okay, so once again, my advice for this reaction, we are not going to do synthesis for this. We could, but once again, the synthesis process that will be from this chapter maybe will be the combination. Did you guys see, like in my previous examples, how I combine 2 steps or 3 steps, right? 3 steps here, another 2 steps, 2 steps, right? In this type of examples, I combine, that will be the maximum that we can do, okay? So I'm not going to really stress you that much with the synthesis, like the conventional synthesis that we have studied before, but my recommendation again and again and again will be to study as much as you can this reaction. So this one is very important. That one condenses all the reactions from this chapter, but in particular for the ones for acid halides and the ones for anhydrides, that will be something that is separate because those are those are the functional groups that have most of the reactions. This one is for acid halides. It's a lot of reactions, okay? And we have a similar one for anhydrides. They're they're almost identical, I would say, but these are more complete tables. Okay, so I would say a skin for acid halides and anhydrides. All right. Okay, so once again, and then just to say goodbye, remember that I'm always available during my office hours, by email, or during lab hours. Okay, so you can always come to my desk while you guys are doing a lab. You know, there is always a reflux, cleaning, or waiting for drying, waiting for the melting point apparatus, waiting for a TLC. You can always take a break and then come to me and ask me questions. All right. So I'll be in touch with you guys soon. Let's just wait. I'm really looking forward for the last chapter about alpha carbon chemistry. Okay. Bye bye.